So I called this more horizontal circles. And the first one I want to look at, example one, first of all, I like this question, I like this question, I like this question. So you probably will see this on a test. Also, I dream of space travel. If you haven't figured that out, Kiefer, I'm a Star Trek guy at heart. And so in real life physics, how would we generate artificial gravity? Well, one way to generate artificial gravity in outer space would be to build a circular space station and spin it. That method will work. It doesn't violate the laws of physics. So here is our space station side view and top view. Supposing this space station has a radius of 35 meters, what does the period of rotation need to be for an astronaut to experience 80% of Earth's gravity? Any suggestions on how I might want to start this out? Dustin, what was that? You know what? I think I'm going to start this with a free body diagram. Which view would work better? I'm going to, I think, do the top view right here. What are the forces acting on this person? Get the obvious. Can I say get the obvious one? Is there gravity acting on this person in outer space? So no gravity. Okay. What else? I'm not sure, but what path is this person tracing out? Where must the winning unbalanced force be pointing? Toward the... So I'm going to draw an arrow pointing towards the center, and the real question is, what force is that? And don't put FC on there. That never shows up on my free body diagram. What force is pushing this person towards the center? That's the question. My block A's got this. I got to be honest. And now I was impressed because it's not that intuitive. What force do you think is pushing this person around in a circle? Yeah. What? What? Are they standing on a surface? There is a normal force. This is the normal force, Fn. So I can now set up an equation. I can say normal force is what's pushing me in a circle. F equals ma. Oh, we're moving in a circle. F equals mac. Which version of AC am I going to use? The one with the V in it or the one with the capital T in it? Well, what's this question asking me to find, Annika? So am I going to use the one with the V in it or the one with the T in it? Okay, so I'm going to get this. Where it says MAC, I'm going to replace that with, don't forget the M, 4 pi squared R over T squared. What about the normal force? How big do I want the normal force to be? I think I want it to be 80% of the Earth's gravitational field. What's your normal? mg? How would I find 80% of that? Yeah, on the left, it's going to be 0.8 times mg. Can little kids and grown-ups go on this space station? Yeah, why? Masses cancel. That's kind of nice. What did you say this wanted us to find? How would I get the t by itself? Well, it's on the bottom. I think I would multiply it to the top over there. I think I would divide the 0.8g down, and that would give me this. T squared equals 4 pi squared r over 0.8g. And then how do I get rid of a squared? Yep. This is how many seconds it should take this space station to rotate around once. Let's plug in our numbers. The period is going to be big square root of 4 pi squared, r is 35, all divided by 0.8 times 9.8. I would strongly encourage all of you to try these ones on your calculator. 4 pi squared r divided by a bracket 0.8 times 9.8 square root answer. You get 13.275, 13.3 units. It's a time. Yep, capital T just means the time to go around once. It's a special symbol. So 13.3 seconds. Cool. Ethan, what does B want me to find? How do I find frequency? It'd be cool if it was on my formula sheet. How do I find frequency? By the way, have you clued in? I think we're on the front page, bottom left corner, yes? Of our formula sheet. How do I find frequency, Ethan, my friend? I don't want T, I want frequency. How about F equals? It's the reciprocal of the period, which we just found in part A. So if on my calculator, I just go 1 divided by, answer button, we would say that this space station needs to be spinning at 0.075 hertz. Cool. What would happen if we, suppose we had a ladder that ran towards the center of the space station? As you climbed the ladder, what would happen to the feeling of gravity upon you? Well, look at this equation right here. As r gets smaller, what happens to the fake normal force that the fake gravity that you're feeling? Bigger, smaller, or stays the same? Well, where is the r? On the top or on the bottom? So as it gets smaller, your answer gets smaller. As you lowered the radius, as you climbed the ladder, you would find yourself getting lighter and lighter and lighter and lighter and lighter. In fact, there would be a certain spot where you would only feel 30% of your weight. What would that radius be? Again, this is a job for a free body diagram, but Dustin, we just did it. I'm going to start with the same equation as before, where I'm going to say m4 pi squared r over t squared. But over here, it's going to be 30% of your weight, 0.3 mg. And again, Dustin, little kids and grown-ups would experience this as well. What's part C asking me to find? Radius. Okay, let's get the r by itself. How would I get the r by itself? Well, divide by 4 pi squared times by period squared. I think I'll end up with this. R equals 0.3 g period squared all over 4 pi squared, I think. I have right now the frequency on my calculator. Because I don't like retyping stuff, I'm going to take the reciprocal of that, and that gets me, Ethan, my period of 13.275, my answer button back again. And so I'm going to write 13.5, but I'm going to use my answer button. The radius is going to be 0.3 times 9.8 times answer button, 13.3 squared. Is that what it was? 13.3 divided by 4 pi squared. I know the answer has got to be smaller than 35, because that's the outer radius of the space station. So if I get an answer bigger than 35, I'll panic because I've made a typo. I get 0.3 times 9.8 times answer button squared divided by bracket 4 pi squared. Uh-oh, my pi symbol didn't go. Pi squared. Ooh, do you get 13.125 even? Nice that it worked out evenly. 13.1. Is that okay? What would happen if you kept climbing and climbing and climbing? Once you got to the center of the space station, what would the force of gravity be there? Prove it. Well, here's what we've been saying. The normal force is what you feel gravity is, and we said that was equal to m4 pi squared r over t squared. Yes? What's r if you're at the center? So if that equals 0, what's 0 times pi squared times 4 times m divided by t squared? Yeah. The normal force would be 0 newtons. That means running along the axis of this space station, you could have a no-gravity fun zone area, maybe. Let's suppose we built a genuinely large space station with a radius of, let's say, 1,000 meters, a kilometer. And that would mean along the center, you could have here's a gravity-free zone where we can come up, we can pretend to fly, we can have some fun there. And just past that, you might have an area where gravity was only 0.1 g, so it would be like everything was a big trampoline-y kind of a thing. And as you move further and further out, gravity would get stronger and stronger. And that's good physics. Now, there is a bit of a problem. I'm going to scroll back. With this particular situation, the space station that I made up had a radius of 35 meters. If I stand up, I'm roughly 2 meters tall. Well, Kiefer is pretty close to 2 meters tall. And 2 meters is a not insignificant portion of that 35 meters. It counts. What you would actually find, and this the movies don't talk about, so typically movies will show a rotating space station. I've seen a few that do it for gravity. Because they got to get all the actors in frame, the radius of those space stations is almost always pretty small. I'm thinking of the movie, for example, 2001: A Space Odyssey, whatever. You would feel in this space station a slightly different force of gravity on your feet than on your head. And so if you face the direction of rotation, you would permanently feel like you were almost about to fall backwards. And so you would probably feel nauseous for quite a while until you got used to it. Now, if we made a space station with a radius of 1,000 meters, well, now your 2 meters is a pretty insignificant portion of that 1,000 meters, and that would work pretty well, but to scale up like that would be a pretty massive engineering feat. Okay? But otherwise, the physics here is pretty solid. So a nice question you might see in the future might be about artificial gravity. And the key to realize is even though I'm talking about artificial gravity, gravity is not on your free body diagram. What's creating the artificial gravity? Which force, James? Normal force, the normal force, the normal force. Another neat example is the gravitron. I like example 2, I like example 2, I like example 2. Example 2 is a nice question. I have to be honest, it is to my shame and embarrassment that I finally only went on the gravitron for the first time 2 years ago. And see, the problem is I go to Playland every year with my physics students, and Playland doesn't own the gravitron ride. The P&E owns the gravitron ride. And so typically, I don't go to the P&E in the summer because I've already gone and I don't feel like paying a bunch of money to go on the same rides. But the gravitron is part of the P&E. So 2 years ago, the wooden roller coaster was down for repairs. And so Playland brought the gravitron out for the physics day because there's some good physics there. I finally went on it. So what's the gravitron? It's a ride that spins really fast and then the floor drops away from your feet so you're pinned against the wall, hovering. The gravitron spins its riders around in a circle if the ride has a radius of 4.8 meters and if it rotates every 2.5 seconds. Ooh. Huh. Alex, what's A asking me to find? the minimum coefficient of friction. It wants me to find, hey, mu. What's mu? I don't know what's mu with you. Which means there's definitely going to be friction in my free body diagram, and I'm pretty sure I'm going to do a free body diagram. They gave me a lovely picture here. Let's do a free body diagram. What are the forces acting on this rider? Let's get the obvious one. Is there gravity? Are we back on the Earth? Which way? Good. Is this person sliding down the wall? Are they sliding up the wall? So that means in the vertical direction, the forces must be, I'm looking for it begins letter B. So I know there's an arrow pointing up. Make it the same size as your mg arrow. What force is that? I'm not sure. I think I know, but I'm going to hold off. What path is this person tracing out? What path is this person tracing out? A circle. So where must my winning force be pointing? Toward the... So I know there has to be a force pointing that way. Which force is that? Ah, that's the normal force, the surface pushing up on me. Any suggestions on what you think that vertical force is then? Ah, that's friction. Would this ride work if you were laying on ice? No. No. We apparently need friction for this ride to work. Okay? This wants me to find mu. I want you to notice there are two equations in here. If you want to, you can do kind of a little line. There's a vertical equation. What's my vertical force equation? What equals what? Yes. And then there is my circular force equation. I guess in this case, normal force is what's pushing me in a circle. For the circular acceleration, I'm going to use the one with the V in it or the one with the T in it. And how do I know? Look at your work, because I've scrolled down. What? How do I know? 2.5. They gave me the period. Okay. Now, the other thing they could have given me is the rotational speed, the centripetal speed, and that I would have used the one with the V. But for now, I'm going to go like this on the right-hand side, m4 pi squared r over t squared. Here, can I put mg? No. Because mg in my free body diagram is vertical, and this is definitely horizontal. That's the no-no. It's still going to be the normal force. I don't know the normal force. And I can't say, oh, but look. I don't know the force the same size as a normal force. I'm kind of stuck. Or am I? Can anybody see how I can be clever? Let me see it. Is that a hand up? Stretch? Ethan, what do you think? The other equation, friction equals mg, why? Friction's got a normal force in it as well, doesn't it? Friction is what times what? Mu times the normal force. So let's try writing that. Mu times the normal force equals mg. And let's get the normal force by itself. How would I get the normal force by itself? I think divide by mu. What does the normal force equal in this particular situation? mg over. So wherever I see the normal force, what can I replace it with? So are you saying that over here I can write this as mg over mu? Hey, Alex, can little kids and grown-ups go on this ride? Really? Why? Well, that's convenient. Grown-ups would feel it more if we were actually calculate the normal force. The m wouldn't vanish, so little kids can handle this ride better than grown-ups for any amusement park ride. The mass doesn't cancel if you actually want to cancel the normal force, but if you can't looking at the other forces, they do. What am I trying to find? Where is the mu right now? On the... Bleh. Oh, wait. I think I'm going to multiply it to the top, multiply the period squared to the top, and divide the 4 pi squared down. I think the 4 pi squared r down. I think I'm going to get this. I think I'm going to get mu equals, is it gt squared over 4 pi squared r? As far as I'm concerned, for the gravitron, I can give you the period and the radius and say find the coefficient of friction. I can give you the period and the coefficient of friction and say find the radius. I can give you the radius and the coefficient of friction and say find the period. Or I could repeat all of that, but giving you speed instead of period. Okay? But the key idea to realize is normal force is what's pushing me in a circle, and friction equals gravity, which means I can get another equation for normal force out of there. It's going to be 9.8. The period was 2.5. Don't forget the squared. All over 4 pi squared. Was the radius 4.8 meters? Which is about right. When I was in the ride, I kind of pasted off quickly. 9.8 times 2.5 squared divided by 4 pi squared 4.8. You get 0.323? Yeah. Now, that's the minimum coefficient of friction. In fact, if we designed the ride like that, you would feel like you were just about to slide down or slide up. You would not feel all that comfortable at all. You would be like, I feel like I'm going to slide. So we would probably double that or make it fairly sticky. But otherwise, you can do that. Although, again, the same situation I mentioned before, the fake gravity normal force he's feeling on his head would be different from his feet. He probably also feels like he's about to fall sideways in one direction. In whatever the direction of rotation is, he feels like he's going to fall in the opposite direction of that rotation a little bit. You have to get used to it. I would love to go on this ride with a bag full of tennis balls and try playing catch with the person across from me. I think we would notice that Coriolis effect that I showed you in the video the other day, where it appeared to us that the ball was curving even though it was going in a straight line. Ooh, what's B want me to find? Speed. How can I do that? Well, I guess I could say acceleration equals acceleration. Circular acceleration or centripetal acceleration equals centripetal acceleration. I could say v squared over r has to equal 4 pi squared r over t squared. You've got to get the same answer both ways you calculate acceleration because they're both legitimate. What's this asking me to find? How would I get the v by itself? What do I do with that r? Yeah, I'll multiply it over, which, by the way, means the r's don't cancel. In fact, I'll get an r squared over there. And then how do we get rid of a v squared? Square root. And this is kind of neat because I can actually do it in my head. Dustin, what's the square root of 4? What's the square root of pi squared? What's the square root of r squared? What's the square root of t squared? And then when I did this, I sheepishly went, wait a minute, Mr. Dueck, you gave me that on your formula sheet. That's the equation for circular speed. I probably could have started right there. But we've also proved then this is why that equation works for circular speed. So it's going to be 2 times pi times 4.8 divided by 2.5. And I get a centripetal speed of 12.1 meters per second, I think, which is 2 pi r over the period. Ooh, what's the frequency of this ride? Ethan, how do I find frequency? Oh, and they told me the period. They said the period was 2.5 seconds. This might even work out evenly. 1 divided by 2.5. Yep, this has a frequency of 0.4 hertz. I'll go 0.40 hertz. If it turns faster, what would happen to the frequency? Would the frequency get bigger or smaller? Well, if it turns faster, what would happen to the period? How long it takes to go around once? Smaller, and since it sits on the bottom, the frequency will get, the bigger this number is, the faster it's spinning. The bigger the period is, the slower it's spinning probably. I already showed you the gravitron picture. Example 3. There was one like this in the homework, or maybe a couple like this, in the homework from last day. I didn't get quite a chance to talk about it. So, it says this, the picture below shows a frictionless tabletop in top view. The mass is 4.15 kilograms. It's attached to a 2-meter long string. It's moving at 2.5 meters per second. It says write force equations and solve for the string tension. When it says write force equations, really that's telling me that this is a good job for what are the forces acting on this? Get the obvious one. Which way? I think into the piece of paper, right? Because it's a top view. What else? Normal force. Which way? Out of the paper towards them. Let's come back to those because they cancel each other out and they're balanced anyways. What else? What path is this tracing out? A circle. So where must my winning unbalanced force be pointing? Toward the... So I know there has to be a force pointing that way. Which force is that? Tension. So if you want me to write a force equation, gravity equals mg equals Fn, but meh. Tension is what's pulling me in a circle. Tension is what's pulling me in a circle. Which version of the AC am I going to use? The v squared over r or the 4 pi squared r over t squared? How do I know? Oh, they gave me, I've got to be fussy, it's not a velocity, it's a speed. So, I can go t equals mv squared over r. The mass is 4.15. V is 2.5, don't forget the squared. All over, r is 2. That capital T, is that the period? It's a tension, and I'm sorry, I used the same letter for both. I apologize. Do you all get 12.96? You know what? 13.0 if I go to 3 sig figs? And it's a force newtons. Well, that's kind of, sort of, kind of cool. But a much neater example is this here, example 4. Turn the page, please. Pause the video. What are the forces acting on this? Get the obvious one. Well, you know what? It's a bit trickier. Let's look at big M first. What are the forces acting on big M? Get the obvious one. So I'm going to call that big M G. What else on big M? Tension. What about on the little ball, little m? Well, I definitely have little mg down and normal force up. But, Alex, what path is this ball tracing out? Where must my winning unbalanced force be pointing? Toward the... So there's definitely an arrow there. Which force is that? Tension. Cool. Evan, what's this question asking me to find? Of? Ooh, what path is the ball tracing out? What's pulling it in a circle? Here's my first equation. I'm going to write tension is what's pulling the little ball, so little m, into a circle. Which version of A am I going to use? Because they want me to find a speed. So little m, v squared over r. On the left-hand side, I don't know tension. Or do I? What's another equation that I could write for the big M mass? What's an equation I could write there? Sorry? Equals what? Is this accelerating at all? So the forces are, I'm looking for the letter B. So as a shortcut, I think I can actually say big mg equals tension, which means I can replace tension with big mg. Evan, what do they want me to find? How? Divide by little m times by, and then how to get rid of squared? And you know what? I'm smiling a bit because I notice I am going to get a square root of grr and other stuff. But the fact that I get that means I probably set this up right. I get V equals big M G R over little m square root. So there's my square root of grr and other stuff. Big M, it says 9 times 10 to the negative 3? No, sorry. 3.6 times 10 to the negative 2. That's 0.036. That's less writing. You can write the scientific notation one out if you want to. R is 0.42. G is 9.8. Little m, it says, is 9 times 10 to the negative 3. That's 0.009, and I'll go with that one. This might work out evenly. I'm seeing a bunch of yucky numbers canceling. It might not. I might have one left over. Square root of 16.4, 4 point something. Oh, doesn't work out evenly. 4.06 meters per second. I like example 5, I like example 5, I like example 5, example 5 is a nice question. The banked corner at angles. Did I say angles? Actually, no, not components. This is about the only time, while you could solve it with components, components are going to be kind of yucky. An engineer is designing a curved exit ramp coming off of a new freeway, and it is true that on-ramps and off-ramps are always banked, as are racetrack corners. Why? She decides to make the corner a banked corner at an angle theta, as shown below. She wants to remove friction from the equation so that the corner will be safe in all driving conditions. Suppose this corner has a radius of 55 meters and theta equals 23 degrees. What speed limit should be posted for drivers? First thing I want you to notice is this. If that's the center of the circle, don't write this down, but we are doing a horizontal circle. Our car is tilted, but the circle itself that we're tracing out is a horizontal circle. And this is still a job for a free body diagram. So, what are the forces acting on this car? Get the obvious one. What else? No components yet. What else? Normal force at right angles, so about like that ish. What else? Let's assume that this road is icy, not a difficult assumption to make today. Okay? Now, normally, I would break this up into components, but there's a better way to do this. Now, if you did break this up into components, you would take that normal force and you would actually break the normal force up into a vertical and a horizontal, because it's this horizontal component that's pushing you in a circle. We don't want to break things up parallel and perpendicular because our circle is a flat horizontal circle, so we want to match it. And it could be done. Instead, do I have two vectors? I'd like to add them together. Any thoughts on how I might want to add them? I think I would choose to draw them tip to tail, you say. When you're drawing vectors tip to tail, always draw the easiest one first, the toughest one second. What's the easiest of those two vectors? Draw that. Now I'm going to draw the normal force, but here's the key. What path are we tracing out? So, when I add these two vectors together, where should my winning net resultant force be pointing? Toward the... And remember, it's a horizontal circle, which means if I stop right there, that can't be right because my resultant is not horizontal. Or if I stopped right there, that can't be right because my resultant is not horizontal. Tell me when to stop drawing the normal force. There's mg, there's the normal force, and from the tail of the first to the tip of the second, there is FC. This is not a free body diagram anymore. The red diagram is the free body diagram, and as always, FC did not show up, but now this is my equation, except in this case, instead of going winner minus loser, I'm saying I'll add them vectorially with trig. Oh, it's been a while. Color, 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 color. Where do you think that theta ends up? Color, 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 color. mg, opposite, adjacent, or hypotenuse? Normal force, hypotenuse. FC, adjacent. Do I know the normal force? No, I mean, I could calculate, but do I know the normal force? No. Do you know which trig function I'm going to use? What it would be really nice to be doing today? Tan. As opposed to shoveling snow or whatever it is. Thomas just got that joke. Okay. So I'm going to have this. Yeah, I know, there's a bit of a delay. Tan, and I'm going to do this generically with no numbers. I guess it looks like tan theta equals opposite. Oh, hang on, Mr. Dueck. I labeled opposite and adjacent wrong. Is that why you're all staring at me? That's opposite. That's adjacent. This is going on YouTube. Wow. Warts and all, I decided that a long time ago. So I'm going to get FC, let's be same color, Mr. Dueck, FC over mg. Get the FC by itself. I'll get mg tan theta equals FC. F equals what? Which version of A am I going to use here? Well, did the question give me or ask for speed or period? I've scrolled down. Speed? V squared over R, and that's going to equal mg tan theta. Ethan, now that you're done yawning, can big trucks and little cars also go on this off-ramp? Really? Why is that? Okay. What was I trying to find? Get the speed by itself. How I'll move the R over. And I heard somebody already say, oh, we're getting a square root of GER and other stuff, but that probably means we're doing this right. In fact, I get this. The maximum safe speed, but also the minimum safe speed, the perfect speed for going around a corner is GER tan theta. And now let's plug in numbers. It's going to be 9.8. What's the radius of this banked corner? 55. Tan 23 degrees. (15.1) or in kilometers per hour. You can take this corner at 54 kilometers per hour. So this could be a corner that you could put in a subdivision and you wouldn't need to put a speed limit. Which force did I not bother including that has often showed up on roadie questions before? Mu is not a force. I didn't include friction. Now, why is that? This is the beauty of a banked corner. Supposing this road is covered in ice, what speed do you hit it at? Still 15.1 meters per second, because I didn't include friction. What if you go too slow? What if it's icy? What? I don't know what that means. Yeah, if you go too slow, you can run the numbers if you want to, but you're going to find you'll slide down. If you go too fast, you'll slide up and off. Now, if we do have friction, by the way, then what I really have is I have one more force, and I can figure out if I go too slow, then friction would be pushing down, and I can figure out the minimum safe speed. If I go too fast, how fast can I go before I overcome friction keeping me on the track? And I can find maximum safe speed, and I could do that. That's a bit more advanced than we're willing to go. So the nice thing about a banked corner is, so too slow, slide down. Too fast, we'll slide up. A banked corner is weatherproof. Whatever, if you're ever doing a banked corner, whatever speed that corner says, if it's a dry day, there's a fair bit of leeway because friction is adding an extra force that I didn't include and it'll cover your butt. Otherwise, though, if it's like wet or icy, do that speed. If you go too slow, you might slide down. If you go too fast, you might slide off. Kind of cool. Turn the page. I'll finish example 6 next class, and we're going to continue the next lesson. Next lesson, we'll look at roller coaster loops, because those are pretty cool too. For now, questions you can start to try. Well, be honest, how many of you have finished the homework from lesson 3 from last day? 1, 2? Okay, I think what I'm going to do is I'm going to press pause and not give new homework today. I'll finish this lesson off tomorrow. I'll give you a bunch, next class, I'll give you a bunch of homework next class. We'll start the following lesson because we're also marking a take-home quiz. Right now, I'm thinking your test on all of this could very well be towards the end of next week or the beginning of the week after. Now, next week, Friday is a Pro D day, so if I could, I'd love to fit it in before then.